The egg dropping problem is the famous puzzle which is often used to illustrate an algorithmic technique called dynamic programming. Being the famous problem, there are lots and lots of YouTube videos explaining this and the dynamic programming way to solve this. But most of the videos stop with it, missing an interesting twist to this problem. And I want to share that whole story in this video. For the sake of completion, I will first explain the popular dynamic programming method and will then move on to our most interesting part. So let us begin. First, let us see the puzzle. We have a building with n number of floors, with the bottom floor being the floor number 1, then floor number 2, and so on till the top floor, floor number n. If we drop an egg from a floor, two possible things can happen. The egg may break or the egg may not break. If the egg does not break, we call the floor as safe floor. If the egg breaks, we call that floor as unsafe floor. The assumption is that if a floor is unsafe, then all the floors above it all are unsafe as well. We have the situation like this. These floors at the bottom are safe and all the other floors are unsafe. Our objective is to find the first unsafe floor. Note that it can be the case that all the floors are safe. In that case, we have to tell that the unsafe floors do not exist. If unsafe floors exist, then we have to tell the floor number of the first unsafe floor. Suppose if you are given only one egg, then to find the first unsafe floor, we have to check the floors linearly from floor number 1, then floor number 2, and so on till the egg breaks. And that will be the first unsafe floor. In the worst case, we have to check all the n floors, so the minimum number of trials needed to find the first unsafe floor in the worst case given only one egg is n, the total number of floors. But we can do better when we are given more than one egg. Suppose we are given enough eggs, say as many as the number of floors, then we can simply do the binary search. Choose a floor in the middle, drop an egg. If it breaks, then check the lower half floors below it. If it does not break, check the upper half floors above it. So each time we can reduce the number of floors by half. So it is basically a binary search. Hence we can find the first unsafe floor in big O of log n trials. But if the number of eggs are lesser, then we cannot afford to do the complete binary search. For example, if we have only 2 eggs and there are 100 floors, then if we drop an egg from floor number 50 and it breaks, then we are forced to check the first 49 floors linearly. It is because we have only one egg remaining. So the question is this: if there are n floors and we are given m eggs, then what is the minimum number of trials needed to find the first unsafe floor? So that is it. Let us try to solve the problem. Let the minimum number of trials needed given m number of eggs and n number of floors be f of m comma n. Suppose if we start by checking the kth floor first, then there are two cases: the egg breaks or the egg does not break. If the egg breaks, then we have to check the bottom k minus 1 floors and we have m minus 1 eggs left. Hence the minimum number of trials needed to check is f of m minus 1 comma k minus 1. So total trials needed is f of m minus 1 comma k minus 1 plus 1. If the egg does not break, then we have to check the top n minus k floors and we have m eggs. Hence the minimum number of trials needed to check is f of m comma n minus k. So the total trials needed is f of m comma n minus k plus 1. In any case, the number of trials needed cannot exceed the maximum of these two. So the minimum number of trials needed is maximum of f of m minus 1 comma k minus 1 plus 1 uh, uh, plus 1 and f of m comma n minus k plus 1. In other words, this is the minimum given we start at the kth floor, and k can be any floor from 1 to n. So if we find the minimum of this over all k, then that will give the minimum trials needed, that is f of m comma n. So f of m comma n is equal to minimum of these elements over all k values. And we know that if we have only one egg, the minimum trials needed is as same as the number of floors, that is f of 1 comma n is equal to n for all n, and obviously f of m comma 0 is equal to 0 for all m. Now we have the recurrence relation and the base cases. Note that this is same as this. So to calculate f of m comma n, we start from the base cases and calculate values in the bottom up manner while also saving those values. From the base cases, we know the values of f of 1 comma 1 to f of 1 comma n. Also the values from f of 1 comma 0 to f of m comma 0. We can save these values in the two-dimensional array. Then using the recurrence relation, we can find the values from f of 2 comma 2 to f of 2 comma n. We save these values in the array as well. We save all the intermediate values so as to use them in the recurrence relation to calculate further values. We continue these calculations till we get the needed value f of m comma n. This technique is called this bottom up method. This technique is called as dynamic programming. Note that in the recurrence relation, we need to calculate the minimum of n elements, which can be done in linear time, that is big O of n. So we need to calculate roughly m into n values from f of 1 comma 1 to f of m comma n, each of which can be calculated in big O of n time. So the time complexity to find f of m comma n is big O of mn square. We can improve this by making an observation. That observation is f of m comma n is always greater than or equal to f of m comma n minus 1. It is because that by increasing the number of floors, we cannot decrease the minimum number of trials needed. So we have this. This means that f of m minus 1 comma 0, f of m minus 1 comma 1, and so on till f of m minus 1 comma n minus 1 is the increasing sequence. And also we have this, that is f of m comma n minus 1, f of m comma n minus 2, and so on till f of m comma 0 is the decreasing sequence. If we note the recurrence relation, we need to find the maximum of these two, and then these and these, and so on till this. These are the pairs corresponding to the pair in the recurrence relation, that is f of m minus 1 comma k minus 1 and f of m comma n minus k, where k ranging from 1 to n. And we need to find the minimum of all these elements. We can also note that f of m minus 1 comma 0 and f of m comma 0 are both 0. Hence we have this inequality and also this inequality. This means that there exists a point where the inequality reverses. That means we have to find the minimum of all these elements. If we look at the lower elements, the minimum of them is this. If we look at the upper elements, the minimum of them is this. So we just need to find the minimum of these two elements. So we just have to get the point where the inequality reverses. And this can be done using binary search. For simplicity, let me explain by employing the colors used here. So we have the orange colors followed by the pink colors corresponding to the different inequalities. We need to find the point where the orange and the pink meet. So we choose the midpoint. If it is orange, then we have to check in the right half. If it is pink, then we have to check in the left half. So at each time we can reduce the problem size by half, which is essentially the binary search. So we can find the minimum in big O of log n time. Hence there are m into n values to be calculated, each taking big O of log n time. So the time complexity to calculate f of m comma n is big O of mn log n, which is the improvement from big O of mn square. So this is one way of approaching this problem, and this is a good example to illustrate the dynamic programming technique. Most of the videos about this problem end with this. Now let us approach the problem in another way, and this is where the story gets interesting. Let us ask the question that what is the maximum number of flows that can be checked given m number of eggs, and we are allowed to do t number of trials. Let that be g of m comma t. So g of m comma t is the maximum number of flows that can be checked with m number of eggs and t number of trials. In our first trial, if the egg breaks, then we will have m minus 1 number of eggs and t minus 1 number of trials left. With that, the maximum number of flows that can be checked is g of m minus 1 comma t minus 1. If the egg does not break, then we will have m number of eggs and t minus 1 number of trials left, and with that the maximum number of flows that can be checked is g of m comma t minus 1. So totally we can check g of m comma t minus 1 plus 1 plus g of m minus 1 comma t minus 1 flows. So g of m comma t is equal to g of m minus 1 comma t minus 1 plus g of m comma t minus 1 plus 1. Now we have a simple recurrence equation. Let us try to solve this recurrence. For the base cases, it is easy to see that g of 1 comma t is equal to t for all t, because with only one egg we have to go through all the flows linearly. So the maximum number of flows that can be checked is as same as the number of trials allowed, and obviously g of m comma 0 is equal to 0 for all m, because with no trials we can't check any flows. Now we have the complete recurrence equation. Consider this. Let us expand g of m comma t minus 1. This gives this, and which is this. Now let us expand g of m comma t minus 2. So we have this, which gives this. We keep on expanding the g of m comma I values till we have g of m comma 0, and by this way we can easily see that this eventually gives summation of g of m minus 1 comma I, where I ranging from 0 to t minus 1 plus t. So we have this recurrence equation. Let us rewrite this t as t choose 1. Now to solve this, let us make an observation. Summation of I choose m minus 1, where I ranges from 0 to t minus 1, is t choose m. It is easy to see why this is the case. Note that t choose m is the number of binary strings of length t that contain m number of ones. Suppose the last one, that is the mth one, appears at I plus 1th bit in the binary string. That means the first I bits contain m minus 1 ones. Number of binary strings of length I that contain m minus 1 ones is I choose m minus 1, and I can range from m minus 1 to t minus 1, as the last one, the mth one, can appear anywhere from 1 to tth bit. Since I choose m minus 1 will be 0, if I is less than m minus 1, we can take that I can range from 0 to t minus 1. This will generalize our result to all possible values of m. So the total number of binary strings of length t with m ones is summation of I choose m minus 1, where I ranges from 0 to t minus 1. So this summation again gives the number of binary strings of length t with m ones. Hence by double counting, this summation is equal to t choose m. Now we have everything in place. From the base case we know g of 1 comma t is equal to t, which is t choose 1. G of 2 comma t is equal to summation of g of 1 comma I, where I ranges from 0 to t minus 1 plus t choose 1. Consider g of 1 comma I. G of 1 comma I is I choose 1. From the summation we have seen now, this is t choose 2. So we have g of 2 comma t is equal to t choose 2 plus t choose 1. Consider g of 3 comma t. From the recurrence equation we have this. Consider g of 2 comma I. This is I choose 2 plus I choose 1. This gives t choose 3 plus t choose 2. So g of 3 comma t is equal to t choose 3 plus t choose 2 plus t choose 1. So it can be easily verified that in general g of m comma t is equal to summation of t choose I, where I ranges from 1 to m. So finally we have a nice formula for g of m comma t. The good thing is that this can be calculated in big O of m time. To see that, we can make some observations. First, t choose 1 is equal to t, and t choose I is equal to t factorial by I factorial into t minus I factorial. With some rearrangement, it gives this. Here, this is t choose I minus 1. So, t choose I is equal to this. Hence, g of m comma t can be calculated by the simple for loop as follows. Now, coming back to our problem of finding the minimum number of trials needed to check n flows given mx, that is f of m comma n, as we have defined earlier. It is nothing but the minimum value of t such that g of m comma t is greater than or equal to n. This is because we need the minimum number of trials with which we can check n flows given we have mx. And note that the number of trials cannot exceed the number of flows. So we have to find the minimum over all t that ranges from 1 to n. So we can simply do the linear search, checking g of m comma 1, then g of m comma 2, and so on till we get g of m comma t greater than or equal to n. This can be done in big O of n steps, and each of the g of m comma I values can be calculated in big O of m time. So f of m comma n can be calculated in big O of m into n time, which is the improvement over big O of mn log n that we got in the dynamic programming. But we can do better. We can get the minimum t value by using the binary search. Choose the midpoint k and calculate g of m comma k. If g of m comma k is less than n, we have to check the right half. If g of m comma k is greater than or equal to n, then we have to check the left half. Continuing this way, we can get the minimum t value in big O of log n steps. So there are big O of log n values to be calculated, and each of which can be calculated in big O of m time. So f of m comma n can be calculated in big O of m log n time. So this is it. This is the significant improvement over the dynamic programming method, which has the time complexity of big O of mn log n. And moreover, we don't need to say the intermediate values. And this is the whole story of this interesting problem. As the final remark, let us consider g of m comma t, which is the summation of t choose I, where I ranges from 1 to m. When m is equal to t, we have g of t comma t is equal to summation of t choose I, where I ranges from 1 to t. This is the famous summation from the binomial expansion of 1 plus 1 whole power t. So this is 2 power t minus 1. So if we have 10x, then within 10 trials we can check 1023 flows. This makes sense because as we have number of x as many as the number of trials, we can afford to do the binary search. So with this, let me end this video. I am happy that I have shared the whole story of this problem with you. Thanks for watching.